Hello students, this is an educational video created by Scholars Academy for ISC Class 11 students. Okay, let's dive right into this exciting overview of motion in a plane. Physics is really all about understanding the physical world around us, and today we're going to see exactly how objects move when they aren't just traveling in a boring straight line. We'll be breaking down some pretty complex 2D concepts into simple, step-by-step principles. Here is our roadmap for today's explainer. We'll start with the basics of projectile motion, move on to key projectile derivations, then solving projectile numericals. After that, we'll tackle uniform circular motion, hit some circular motion numericals, and finally wrap up with a summary and conclusion.
Section 1. Basics of projectile motion, the parabolic path.
So you know when you throw a ball and gravity pulls it down at a totally different angle from your throw. It doesn't travel in a rigid straight line, right? Instead, it creates this beautiful mathematical curve called a parabola. The absolute crucial point here is that we have to mentally separate 2D motion into two distinct 1D motions. The x-axis motion is perfectly uniform, while the y-axis is constantly being accelerated by gravity. Think about it. In the horizontal x-axis, there is absolutely zero acceleration. Because of this, the horizontal velocity, which is u cos theta, stays perfectly constant throughout the entire flight. But on the y-axis, we've got an initial velocity of u sine theta fighting against the constant downward drag of gravity, which we call minus g. By splitting the motion up exactly like this, any giant 2D problem literally just becomes two simple independent 1D problems.
Section 2. Key projectile derivations, mathematical proofs.
Let's see how those independent 1D motions actually build our core formulas for flight. By applying the standard equations of motion just to the vertical y-axis, we can derive the time of flight. This isolates exactly how long our object stays in the air. Now we know that at the absolute highest peak of its arc, the vertical velocity becomes zero for just a tiny fraction of a second. By calculating the time it takes to reach that peak and simply doubling it, we arrive at this totally elegant formula. Capital T equals 2u sine theta divided by g.
Moving on to maximum height and horizontal range, it's kind of fascinating to see how the launch angles play out. The maximum height formula uses sine squared theta, while the horizontal range formula uses sine 2 theta. And since the maximum value of sine is 1, which happens at 90 degrees, your maximum distance, or range, will always occur when you launch at exactly 45 degrees. Here's a really cool trick though. Thanks to the symmetry of the sine function, throwing an object at 30 degrees yields the exact same horizontal range as throwing it at 60 degrees. Literally any two complementary angles, like say 20 degrees and 70 degrees, will land in the exact same spot.
Section 3. Solving projectile numericals, application in action.
Now that we've got our mathematical derivations, let's ask ourselves a classic exam question. What happens when our initial vertical velocity is exactly zero? Picture this. An object is fired purely horizontally at 98 meters per second from the top of a 490-meter high hill. The standard formulas we just learned? They won't work straight out of the box here, because the object wasn't launched from the ground at an angle. We're going to need to rely on our foundational physics principles to solve this one. Let's break it down. Looking at our given data, there is zero initial vertical speed. The initial horizontal speed is 98 meters per second, and the vertical displacement is minus 490 meters. Using our core formula for the y-axis, which is the second kinematic equation, we can calculate a 10-second fall. Once we know the object is falling for exactly 10 seconds, we just multiply that by the constant horizontal speed of 98. That gives us a massive 980-meter horizontal range. Now for the final velocity. The horizontal component stays at 98. Using the first kinematic equation for the vertical drop over those 10 seconds, we get minus 98. So our final hitting velocity vector is simply 98I minus 98J. Section 4. Uniform circular motion, spinning dynamics.
All right, pivoting to the second major concept in this chapter, we have uniform circular motion. Now, here's the catch. Even if the speed is perfectly constant, the velocity is never constant. Why? Because the object's direction is changing at every single millisecond, making it an accelerated motion. Think about it. Speed is just a number. It's a scalar, but velocity is a vector, meaning it deeply cares about direction. If an object is running in a circle at a steady 5 meters per second, its speed is constant for sure. But because it's constantly turning, its velocity is constantly changing. And in physics, a changing velocity means you have acceleration. Period.
So here's your core vector toolkit for circular motion, linking linear velocity with angular velocity and introducing the center-seeking centripetal acceleration. Angular displacement, or theta, is measured in radians. Angular velocity, which we call omega, tells us exactly how fast that angle is sweeping per second. The ultimate bridge between the linear world and the spinning world is this beautiful equation, v equals r times omega. And finally, that acceleration we were just talking about, that is centripetal acceleration. It's always pointing directly to the center of the circle, and it's calculated as v squared over r.
Section 5. Circular motion numericals, ratios, and rotations. Let's put these spinning dynamics to the test with a brilliant conceptual riddle. Which has a greater angular velocity, the tiny hour hand of a standard watch or the entire planet Earth spinning on its axis? Keep in mind, we aren't talking about linear speed here. Obviously, the Earth is hurtling much faster through space. We're strictly asking which one completes its 360-degree rotation faster. Based on our given parameters, the watch completes a full cycle in 12 hours, compared to Earth's 24 hours. Applying our angular velocity formula, omega equals 2 pi divided by the time period, the math proves the watch is actually twice as fast, giving a 2-to-1 ratio. Think about it. The hour hand takes 12 hours to do a full lap, while the Earth takes 24 hours. Therefore, the tiny hand on your wrist actually possesses a higher angular velocity than the massive planet you're standing on.
In this next numerical, we're given a mass of 10 kilograms, a radius of 0.2 meters, and a frequency of 1,000 revolutions per minute. Applying our formulas to find omega in seconds, by converting that frequency, we calculate an omega of 100 pi over 3. Multiplying that by the radius gives us a linear velocity of 20.93 meters per second. Finally, plugging that velocity right into our centripetal acceleration formula yields a totally massive centripetal acceleration of 2187.5 meters per second squared. This really goes to show how incredibly high acceleration can get when an object spins rapidly in a tight circle.
Section 6. Summary and conclusion. Bringing it all together. We've covered a ton of ground today, from parabolic trajectories to extreme centripetal forces. So let's synthesize these core physical principles. The biggest takeaway? Always separate 2D motion into isolated axes, and keep in mind that circular motion is strictly accelerated due to those constant directional shifts. Projectile motion is literally just a puzzle combining uniform horizontal gliding with standard vertical gravity. Uniform circular motion might sound perfectly steady, but the constant change in direction means centripetal acceleration is constantly pulling the strings. And a vital final tip for your exams, the standard kinematic equations we used for projectiles are utterly useless for uniform circular motion. Don't mix them up.
I'll leave you with this. If both projectile and circular motions rely on constant acceleration vectors, like gravity and centripetal force, what complex paths emerge when we combine them both? Imagine a spinning object that is also thrown through the air in a parabolic arc. Think about that question as you practice your homework, keep pushing your boundaries, and as always, happy studying from all of us here at Scholars Academy.